Hello, everyone. Thank you very much for being here. My name is Jordan Alexi Caraballo-Vega, and I work for the Science Data Processing Branch and the NASA Goddard Space Flight Center. This work was done in collaboration with Elizabeth Webb, which is a PhD student from the University of Florida, and the NASA Center for Climate Simulation, which is our supercomputing facility. The motivation behind our work is that we want to see what is the potential of Max RCNN, which is a deep learning object detection algorithm applied to very high resolution satellite imaging. We're talking about like half meter, 1 meter resolution data that we acquire from Worldview via the Maxar agreement. And we have been doing semantic segmentation of the satellite imagery for some time now, doing random forest, LSTM, and fully convolutional neural networks, such as UNIT. And we have found that it is actually efficient, and we are able to segment pretty accurate some of the regions that we're looking for like land cover and land use change detection. Now, there are some features that sometimes semantic segmentation is just not ideal. Like we're looking sometimes at features that are just big in size that we just have a couple of occurrences of them, and we only care about like the boundaries of those objects and not only like those individual pixels that we're looking for. So when Elizabeth came with this problem, which is identifying tall slumps in Alaska, we thought that the master CNN algorithm would actually would have potential for the use case. And the first thing that we do is that we gather the data and we pre-process the data. We auto rectify, pan sharpening, and Thaw reflectance. And then we gather composites of 3 bands for the data set. So we get RGB, blue, green, red, and then red, neon for red, blue, so we can identify what are the difference of using different bands when feeding the master CNN algorithm. And once we have our data pre-processed, we went ahead and manually annotated labels. And the master CNN algorithm takes into account the COCO dataset format. So we create a JSON file that adheres as it takes the bounding boxes and also the binary mask from the just annotated labels. So you have now your data set, which is the raw data pre-processed, and then you have the actual bounding boxes and binary mask that you can process. And just to provide some details on the back end of things and the engine of running these algorithms, we created several containers with the drivers included, so we could make this data set, well, not the data set, but the software involved portable, and it could be used in other places. And our main backend is NVIDIA Rapids framework, just to accelerate the software with GPUs, but we also use the PyTorch backend for the deep learning application. And we are leveraging NASA Center for Climate Simulation GPU resources. Yeah. So once you have the container, it can be actually portable in the case you have NVIDIA GPUs on your cluster or your university cluster. Once we have the environment set up, we go ahead and start training. And the main idea of the master CNN is that you identify a region of interest. You identify then a bounding box for that region of interest, and then you create the instance segmentation mask for the particular objects that you're looking for on that bounding box. And what we do is that we do transfer learning. We start from the ImageNet weights, and then we train from there. So we can use those features that have been learned already from the ImageNet network. And we found out that at least the accuracy for the bounding boxes or for the identification of the region of interest is pretty high. Like we got, at least during training and validation, we got 100% accuracy on the bounding boxes just by identifying the region of interest. And then we got accuracy above the like close to 90 and 80% when we were dealing with identifying the individual boundaries of the objects. So let's say the insect segmentation part of the master CNN. So the model was able to identify the location of those Thaw slumps, but then it would miss some of those boundaries or edges when trying to identify the actual instance segmentation of it. Um, the application of deep learning, we use tiles. We don't use like the whole regions. So we developed software so we could classify entire regions by using sliding windows. And ideally, you wouldn't get any artifacts by just using windows that are adjacent, but sometimes there are artifacts. So we're using two-dimensional splines or splines of second order to smooth out those edges between tiles that are adjacent. And once we have this software in place, we go ahead and we classify the region that we're looking at right now. And in a future work, we're gonna expand to like more dates and even more regions. But right now, our main sub-region is in Alaska. And there are some examples at the left side of the poster where we were identifying as a 100% accuracy the bounding boxes of those slumps, and then failing to identify some of those edges or borders of the slumps. And our main goal, at least, we identify that this master-Sinan algorithm has potential for these particular data sets. We can actually apply this algorithm for very high resolution data, and it actually it did better than we were expecting, because we were expecting challenges and problems because of like data contamination or even like the spectral diversity in the particular pixels that could be in these slumps. As future work, we plan on increasing the training data set that we're using, so we can move to like a wide diversity of dates, and we can generalize the model better. And then we also want to improve how the models identify some of those boundary regions. Uh, Other than that, thank you very much for listening in. And again, like the links are on the poster, so feel free to gather the links and download the containers or the software in case you want to use it for your custom data sets. Thank you very much.